Hello, my name is Grace Lewis, and I'll be talking to you today about characterizing and detecting mismatch in machine learning enabled systems. This is joint work of my colleagues Stephanie Bellomo and Ipe Koskaya. The motivation for this work is the following. When you think about how ML-enabled systems, or ML systems for short, are developed, they typically involve three different and separate workflows. You have data scientists who are mostly trained as statisticians that are developing a trained model. Then that trained model is passed on to a software engineering group for integration and testing into a larger system. And then typically that model is then passed on to an operations group for deployment and monitoring. What happens is that if you think about how these three groups are, they're very different. They have different perspectives, they have different processes, and sometimes they even have different vocabularies. So what happens is that this can lead to independent decision-making based on incorrect assumptions about realities of the system. We call this problem ML mismatch. So therefore, we define ML mismatch as a problem that occurs in the development, deployment, or operation of an ML systems that is due to incorrect assumptions that different stakeholders made about different parts of the system. In addition to that, we posit that ML mismatch can be traced back to information that should have been shared between stakeholders, but was not shared. And if they would have shared that information, the mismatch or problem would have been avoided. So common examples of mismatches are, for example, that the computing resources required to serve the model are very different than the resources that are available in production, or that training data is very different from operational data, or that the model APIs are very different from APIs of upstream and downstream components, or, for example, that the metrics that are required by the data science team for troubleshooting and retraining are simply not available from the monitoring infrastructure. In order to better understand this problem, we developed a set of three research questions. The objective for this particular project was to develop a set of machine-readable descriptors for ML system elements that would codify that missing information that I talked about earlier that would have to be made explicit to avoid mismatch. The research questions therefore defined are, first of all, what are common types of mismatches that occur in the end-to-end development of ML systems? Second, what are best practices for documenting data, models, and other system elements that will enable detection of mismatch? And finally, what are examples of mismatch that could be detected in an automated way based on a codification of these best practices in machine-readable descriptors? In order to do that, we divided our study into two phases. In phase one, and I'm going to talk about a part of phase one today, what we did was to answer RQ1 about what are common mismatches, we identified examples of mismatches and their consequences via interviews, and then we validated these mismatches via a practitioner survey. In parallel, we did a multivocal literature study to understand those best practices from machine learning systems, in particular as it refers to documentation and information that should have been shared. Again, today I'm going to talk only about the left side of this diagram. We conducted 20 interviews. Out of those 20 interviews, we obtained 140 examples of mismatch, and then we were able to break those mismatch examples down into 232 instances of information that was not communicated that led to mismatch. This slide also shows the diversity in affiliation as well as the primary role of the people that we interviewed. Out of the codification process of those interviews, what came out is the following. 36% of those pieces of information that were not shared had to do with trained model. 60% had to do with operational environment, 15% with task and purpose, which we see basically as the requirements for the model, 10% raw data, 9% development environment, 8% operational data, and then 6% training data. What I'm going to do in the next slides is break these categories down. So when it comes to trained model, most of the mismatches had to do with lack of information about test cases and test data, followed very closely by lack of model specifications and API. The test cases and test data is important to bring out because in general, the mismatches had to do with the fact that once a model was delivered from a data science team to a software engineering team, the software engineers simply had no idea how to test the models. How do they make sure that the model is properly integrated? What are good test cases or good data to find out if the model is integrated correctly? As far as operational environment, most of the mismatches had to do with runtime metrics and data. In this particular case, most of the examples had to do with the fact that the data scientist needed a specific set of runtime metrics and data to be able to do not only retraining but also troubleshooting. And simply it was information that was not being collected by the operational environment, and therefore they didn't have the information that they needed. As far as task and purpose, this was more evenly distributed than the other categories. Most of the mismatches really had to do with lack of knowledge or of business goals or objectives that the model was going to help satisfy. This is actually very interesting because it was one of the best quotes that we got from our interviews, and we believe is one of the major causes for problems. A lot of times data scientists are simply given data and they say, hey, go do some good data science to this data, but they don't know what is the problem that they're solving. And so basically what is happening is that the problem specification task is being left in the hands of the data scientist, which is good for in some ways, but not so good in others. So definitely communicating business goals, success criteria, usage context is very important for data scientists to develop models that actually solve problems. As far as raw data, most of the mismatches had to do with lack of metadata, in addition to lack of something similar to what in software engineering we call the data dictionary. This was a little bit surprising to us because we expected more of it to have to do with the data dictionary. So when you look at data, what are the field names? What are the descriptions? What are the values? What do null values mean? Which is something that is very important for a data scientist. But the data scientists also said that a lot of the problems were caused by lack of metadata, not only the syntax, but more like the semantics. How was the data collected? When was it collected? What is the distribution of this data? What is the geographic location if that is important? What were the time frames? Was there any seasonality effect in the data? So having that information, the metadata, was even more important than having a data dictionary to know what are the outliers, what are you lacking, what are the variables mean, etc. As far as development environment, most mismatches had to do with lack of information or shared information with respect to programming languages, frameworks, tools, and libraries used in the development environment. We found several mismatches related to this category, in particular in environments where the model had to be ported from one language to another. For example, we know that in data scientists, it's very common to develop models using R, but then in production, often these models have to be translated, for example, to Python, which is much more used in production. And so a lot of the mismatches really had to do with just problems in the porting process, just because there wasn't enough information shared about what were the programming languages used, the tools and libraries and things like that. A very interesting example, for example, came up where floating point, the way the floating point numbers were handled was very different in R and Python, and they were getting errors and they didn't understand why, and they doing some troubleshooting, they realized it was difference in libraries. As far as operational data, most of the mismatches had to do with lack of information sharing about data statistics. What is really important here is that when we think about how these systems are developed, in particular the model part, data scientists are provided data in a flat file, in a database, in some type of, I would say, static data source. But once the models are deployed, the data is coming from a live system. It's either coming from a sensor, it's coming from another system, it's coming from manual input. But the difference, not knowing these statistics about the data, like what the actual data looks like when it's in the operational environment, is very important for data scientists to be able to develop proper models. So, for example, being able to understand the rates at which the data is coming is something that also led to mismatch, or being able to understand what does the data pipeline actually look like when the system is operational was something that led to a lot of mismatches. And last but not least, as far as training data, most of the mismatches by a lot were related to data preparation pipelines. In particular, a lot of the mismatches had to do with where does the data pipeline end and where does the model start? Or said in a different way, how much of the data preparation and cleaning is done inside the model component, and how much of that has to be done outside of the model component, because in any way in the operational system you have to be able to replicate that data pipeline, whether it's separate or part of the model component. So a lot of the mismatches here had to do with that specific idea of knowing when one begins and the other one starts. To be able to validate our work, we conducted a survey. Where we had 31 survey responses. About half of them were people from the original set of interviews, and the other half were new people from the same or different organizations. And this chart shows some of the demographics for the people that responded to the survey. The nice thing about the survey is that for all categories, most respondents rated the importance of sharing information about each of these items as important or very important, which to us is good because it means that the information that we codified is definitely relevant. An observation, there are other observations in the paper, and later I'll show you how to get to the paper. Not surprisingly, what varies is important per role. So for example, if you look at programming language, very important for operations, not so important for data scientists. Computing resources, obviously very important for operations and development, less important for data scientists. But I think what this means is that definitely it validates what we're doing, that it's even more important, that sharing this information is important because not for everybody it's as important, and therefore they pay less attention to this when they're doing their part of the system development. We're happy to inform that phase now is not complete. It was not complete. It was not complete by the time when we submitted the paper, but now it is complete. And what we've done after that with the information that we had is that we took the validated mismatches and consequences from the survey, as well as the ML system element descriptors, or the attributes that came from the multi-broker literature study, and we did a mapping between the two. So basically, for each mismatch, what is the information that you would need in order to avoid having this mismatch? And then we did a gap analysis. Which mismatches did not map to any attribute, and which attributes did not map to any mismatches, and we filled in the gaps. And out of that, what came was a descriptor formalization. We codified the resulting attributes into JSON schema, descriptor specifications, and created sample instances for these descriptors. Our vision is automated mismatch detection, and that is why we emphasize so much on them being machine readable, because we want to be able to build tools that can use these descriptors in order to detect mismatches. And some examples of tools, for example, something that would be very simple would be like a web client that simply reads in all these descriptors and is able, based on some of the rules that we established when we did the mapping, say, okay, there's a mismatch here because these two values don't match. Or being able to use them in operations, like, for example, the tool at the bottom, which is a distribution monitor, which is using descriptors from the training data to be able to look at the distribution of the data during training and compare it to the distribution of the data that it's seeing in operations. Next step for this work, we're going to publish the full study and the descriptors. That should be coming very soon. And also very good news is that we received funding to continue this work starting October 2021. Where we're going to develop an automated mismatch detection tool so we can support larger scale validation of the descriptors, validating with real users and real systems. And also, because the lack of test cases and test data was the number one cause for mismatch, we want to be able to extend the descriptors to support testing of production readiness of ML components in the form of a testing assistant of some sort to help data scientists as well as software engineers make sure that their models are production ready. A reminder that the replication package for the reported part of the study is available at github.com/jalewis/mlmismatch. And at this point, we are happy to take any questions. Thank you.